Everybody, it's Eugene Lee Show. A couple of weeks ago, I launched Recon 3D, which is an iPhone scanning app that uses the iPhone's Lidar and fuses it with photogrammetry. Now, during the webinar, I played a number of clips from different people, but one in particular was from Jared Heinly, who is the chief scientist at EveryPoint. And I only had time to play a couple minutes or little clips from our full interview, but I did say that I would post the full interview in its entirety. So without further ado, this is the full interview that is uncut and unedited with Jared Heinly, the research scientist at EveryPoint. Hey, Jared, thanks so much for being here today. Really appreciate your time.
Yeah, thanks for having me.
All right. So I want to start with your background, and let's go back before you were, studying that. And were you the kid that was into the little, the digital stuff and the tech stuff? Were you that kind of kid?
Yeah. So growing up, my dad was an electrical engineer by trade, and then eventually switched into computer science. So growing up, I was always surrounded by electronics, and we had a computer in our house. And so that was always just fun to tinker with, trying to make, can I connect a battery and a light bulb and a fan and just, switch and just try to understand electronics. That was really fun. Eventually got, I love playing on the computer, trying to figure out how to use the computer. What really sparked my interest was when I got my first TI, Texas Instruments graphing calculator, like a TI-83 in school. And first thing I did was put games on it. Play Tetris, play whatever. But then I was like, how do you make those games? And so that's what sparked my interest. Like, let's make games, get into programming. And then very quickly, then I was like, well, I don't want 2D games. I want 3D games. How can I write 3D games on a calculator? Well, that didn't go so well. So then that's like, I need to learn, I learned Java. I need to get on a computer. I need to actually learn programming. And then from there on, it was just, undergrad, grad school, just digging into 3D programming.
So you knew, so you knew what you wanted to do. And then, so you went to the University of North Carolina, Chapel Hill. Yep. It's a computer science department, right?
Yep, computer science department.
Okay, and you did your, now did you finish your PhD? Was it 2015 or 2016?
2015.
Okay.
Got my PhD there.
And it was, your thesis was toward efficient and robust large-scale structure from motion systems, right? So
yes,
you were interested in, I guess, masses of images from people, and I've looked at some of the papers that you have as well. Like you've done stuff like with trying to reconstruct, there was something you had, maybe you can tell me about it too, but reconstructing the world in 6 days and that sort of thing. But let me start with your PhD. So tell me what that was about.
Yeah, what that was about. It was, so the research lab that I was in, we focused on, it primarily had a focus on large scale, computer vision. When I had joined the group, they had just finished a work on building Rome in a day. The title of the paper was called Building Rome in a Cloudless Day, because they were talking about, we can take millions of images from Rome and process them on a single computer within a day. And so I entered the group. They had just come off of this, amazing work, and so then my task was, well, what's next? And so then it was just exploring what are different things that we can do to improve the 3D reconstruction of these really, really large data sets, really large being millions of images. At the end of my PhD, I was dealing with 100 million images on a single computer, trying to figure out how can you make sense of such large data sets, and what sort of problems do you encounter? Because one, you have problems of scale, figuring out, how can I handle so many images? How do you even make sense of so many images when you can't fit them all in memory at once? You've got to use streaming, you've got to use caching, you've got to use some sort of other data structures to make sense of that. And then other problems you just find in just, with having so many photos, like if you've got the same, same repetitive structure. It's the same light post in multiple locations. It's the same billboard in multiple locations. How do you distinguish between these, repetitive recurring structures in natural environments? It's not a lab setting. Everything isn't nice and controlled and only seen from one angle and one viewpoint and one instance. We were downloading, random photos from all over from all over the world.
Yeah, I remember a while back there was something when Microsoft announced they had that photosynth they called it originally, and so they were trying to do. I remember they did. I don't remember which cathedral it was, but it was a cathedral that they had reconstructed from a number of like Facebook or tourists, photos that were online. So I mean, obviously, what you're talking about is much more large scale. So is the problem with that sort of thing the because it sounds like the problem is not the so much the photogrammetry component of solving camera parameters and all that thing. So is that kind of licked that part, but it's really now like you're talking about like the memory issues and some of the other problems that you have by using all these multiple these unknown or uncalibrated images.
Yeah, that's a great insight, and that really is what a lot of my work has been. It's been working around photogrammetry. So I haven't been improving, the low level, implementations of a structured motion system. I will get in there, like if there's something I want to accomplish. Oh, I want the bundle adjuster to be doing something different, or oh, I want to be optimizing a different residual within that, central matrix solver or reprojection error or something. Like if there's something that I want to tweak in the algorithm, I'll get in there and do that. But a lot of the work is saying, well, okay, and now that we've got these core photogrammetry algorithms, how do we work with them to enable these bigger applications?
Okay.
How do I organize the data that goes into it? How do I deal with the various artifacts that could occur, or the various edge cases that might pop up as you start to work with the photogrammetry algorithms?
Okay, so I obviously see it's like a perfect fit with EveryPoint, and actually, well, I should say before EveryPoint, it was now when you started, was it URC Ventures or was it robotics or I can't remember the name.
Yeah. So yeah, when I joined, we were URC Ventures,
Okay.
and then when we changed over to EveryPoint.
Okay, and I mean, obviously now that's a huge component. The photogrammetry component is still something that you guys were doing, and you were working a lot with video. So, just very briefly, I know what you guys. One of the products or one of the things that you guys do is sort of having people walking around whatever stockpiles or something, right? And then they are able to produce some kind of let's say a calculation of how much inventory they have, for example, right?
Yep.
Okay. So like with something like that, like where you're using video, were there any kind of challenges that you had there? I mean, because you were just using video and pulling frames. I mean, what kinds of things came up there that you found were like, hey, I didn't think that was going to be an issue, but it turns out being a problem.
Yeah. So some of it is just, especially with with the video case talking about, you're hinting at stockpile reports. So trying to measure, in this case, stockpiled material or other materials for inventory from these video collects. And one of the challenges we ran into there was just how do you train someone to do a good collect? Because for myself, like for me, like when I approach a scene that I want to capture for photogrammetry, I sort of intrinsically know, oh yeah, I'm going to make sure I have good overlap and clear photos and get different angles and perspectives. But if I just hand a phone to some random person and say, hey, go record a video of that pile, they're going to walk around their pile and record a video that's very different, than what I would have done.
Right.
And so part of it is, customer education, trying to train someone on the best walking strategies, best capture strategies. There was also a huge piece in just making the algorithms more robust, saying, okay, if someone stood still and rotated the phone in place and just looked around in all different directions, that's going to be bad for photogrammetry. But through some intelligent frame selection, we can help recover from that, or even using some sensor fusion, so pulling some inertial sensor data off of the phone or device. We can help use that to augment our reconstruction capability to work around some of those problems.
Right. Well, I want to get into the EveryPoint stuff, and you said the magic word, which was sensor fusion. So that to me is really interesting because of what you guys are doing with the new iPhone Lidar and the other sensors that are on the Apple iPhone and stuff like that. Let's break it apart. So let's talk about just the Lidar. And let's say, for example, if you just were using Lidar, what kind of information do you get out of the Lidar sensor, or what kind of information does it provide you that allows you to do different work with it?
Yeah. So at the moment, so the LiDAR on the Apple sensor, it provides us with depth readings, rather low resolution. It's like 256 by 192 pixels resolution depth readings from that. So which gives us sort of for free depth estimates of what's in that scene. And so that can be used to accelerate a lot of different algorithms or processing. When we're trying to infer, well, what is the final depth of the scene? What's its 3D shape from different angles? And gives us the ability to, in environments where a photo-based reconstruction algorithm may have failed, like a blank wall or textureless surface, where I can't actually distinguish one pixel from the other, that depth sensor is able to give us a depth reading and help recover those depths.
So when you talk about, like, when people talk about a depth map, is it actually providing you an image, and inside of those image, like you talked about 256 by 256 or something like that, and each one of those regions or cells is actually some kind of a distance. So it's like is it a two-dimensional representation of the sensor with a depth associated to that? I'll call it a pixel, but to that volume of space.
Yes, yeah, you're exactly right. So yeah, it's a two-dimensional representation, where each so it's like an image, where each pixel in that image is the depth, along that viewing direction. So that top left pixel might be, is looking up and to the left. And it's going to say, okay, that depth is some floating point value, 1.2. Okay, it's 1.2 meters in that direction. The next pixel beside it, 1.15. Okay, 1.15 meters, and so on.
Okay. And so now, there's the photogrammetry side. So you guys are doing stuff with photogrammetry, which is video. Like, I mean, obviously you can take photos, but a lot of it's efficient to take videos because you get all these multiple frames, right? I think that's one of the advantages, is that you can, instead of a person going here and then they forget to take another spot, whatever, every time they're moving their phone, they've got a position. But there's also problems with that. So I've seen people holding the phone and they've had too much caffeine and they're doing this, all right? So that doesn't work. Maybe it doesn't work out so well. What are some of the like intelligence, or what kind of things are you putting into, or you're doing to the video that helps with the photogrammetry reconstruction?
Oh yeah. So with that, we've put a lot of work into that, and so that's one of our core patents that we have as a company, is around taking this stream of imagery, so a video, stream of video frames, and figuring out which ideal subset of those frames is best used for 3D reconstruction. So things that we're looking at there is first I'd say is like connectivity, making sure, or connectivity and overlap, making sure that the set of frames that are selected from that video, maintains connectivity. Because as you said, if we have someone just taking photos, they might have forgotten to take a photo in between, two positions, and all of a sudden, these two photos don't have enough overlap, and we're not able to match them to help our 3D reconstruction. So the video, we're automatically able to select, a set of frames that have good overlap between them. Okay. We're also able to look for things like image sharpness or clarity or blur. In that case that someone is, shaking their hand, or maybe they're trying to hold steady, but all of a sudden, their foot, gets caught on a rock, or they step in a hole, and the phone bounces. So those sort of parts of the video where there is a lot of blur or a lot of shake, we can skip over that and reacquire and say, okay, well, we were tracking the scene really well. Oh, all of a sudden the user moved their phone, but then they came back to sort of where they were and then kept going on. We can automatically link those two parts of the video and skip all of that sort of messy stuff in the middle.
That's interesting. And can you say something about how it actually looks for the blurring, sort of in a more of a simple way? Like, when it's looking at, like, how does it determine what is crisp and what is not crisp? That's kind of interesting.
Yeah. So a lot of that comes down to I call an image filter, but it's looking at the pixels. And so what we'll do is we'll compare, one frame in the video to other frames nearby it. And so saying, can I see sharp edges or crisp points, saying, oh, here's a dark pixel that's right next to a light pixel. If I see high contrast pixels near each other, then I can infer that might be a less blurry image, as opposed to one where it's like, well, it's dark and then it's dark gray and then it's medium gray and light gray, something where there's not as sharp edges, not as sharp contrast. You get sort of smoother transitions in the colors. That's one way to kind of infer that, okay, this frame is sharper or crisper than this other image. Okay,
so you have some kind of threshold, and then if it's below that threshold, you keep it. If it's above or whatever, then you can kick it out, type of thing.
Yep.
Okay. So you alluded to some of this before, but now let's say now we start bringing these two together. And, photogrammetry has some weaknesses. So for example, you're doing a beautiful, brand new, shiny
car and it's just been waxed and there's all kinds of reflections and shiny spots. It doesn't, and it's not a criticism of any one particular product or whatever, but every photogrammetry program has a problem with it, right? It's just the nature of the beast, the way it is. And then on the other side, the LiDAR sensor, one of the things that we've seen is if you're just using LiDAR, you tend to get, it's fuzzy. So, the data doesn't look crisp. It looks fuzzy, it looks noisy. And, sometimes depending on the app or whatever that you're using, there may not be loop closure and things like that. So the one thing that I'm noticing when using, when creating these things now with Recon 3D or with the EveryPoint app is that the data is clean. It's much cleaner than what I would have expected. And in fact, I've looked at a comparison between what we're getting out of the app versus, some different just photogrammetry programs, and you can see that there are some advantages. So to make a long story short, or what I'd like to know is how does one help the other, and like what are the circumstances where like this is a weak point here but it helps here kind of thing?
Yeah, great question. So I think you already hit on sort of the two key pieces there. One being loop closure, and then the other being that sort of that fuzziness or the noise, and the contrast with it being clean and the results that you're seeing. So I'll start with those two pieces. So one with loop closure. What's nice with photogrammetry is that photogrammetry, I call it an offline process. It's once you've captured all of the data. You finish your data capture and then you begin the processing. And so photogrammetry has the ability to look at all of that input imagery, look at all that input data, and then make its decisions based on that best sort of global understanding of everything that's been received. And so if you were walking around, a car or a vehicle, you're going to have perhaps, one loop around that vehicle, two loops around that vehicle, something like that. And so photogrammetry is able to say, oh, okay, well, I see these multiple loops. Here's an image that sees the front of that car from two different elevations or a few different angles. Let's use all of that imagery to help estimate the best camera position, that gets camera pose in that reconstruction, to get that result. And with that sort of global reasoning, we use the word called loop closure. So automatically being able to detect, when the camera has returned to a similar position, closing that loop. We're able to, photogrammetry is able to, perform that reasoning, detect that these images are from the same area, and then have those images align. That's in contrast to what I'll call more online techniques. So something like SLAM, simultaneous localization and mapping. The concept in SLAM is as you're walking around, as the phone is moving in space, it's continually figuring out, what is the position of that phone. I said phone, it could be camera, whatever it is, whatever device it is that's moving around that camera, continually estimating what its position is. And one of the challenges there is because it's delivering these online results, it's not able to perform that global reasoning at the end. It has to make sometimes some shortcuts or some assumptions about, well, hey, here's where I've been, here's where I am now. I need to deliver a result. Let me deliver one. But you may start suffering from issues like drift, which a lot of times with, I'll talk about the iPhone specifically. If you're using a scanning app that's purely built on the LiDAR sensor and ARKit, which is a SLAM engine, you're going to see things like drift, missed loop closures, because it is a SLAM implementation that's not performing the same amount of loop closure or adjustment, as you return to common locations.
Yeah. Okay.
No,
go ahead. Please.
I was gonna say, yeah. So with the loop closure, so the one of the benefits you get is that loop closure, being able to remove these obvious misalignments. The other real key piece about why the results that you're seeing that are cleaner is just due to our algorithms. So we've spent a lot of time optimizing our photogrammetry algorithms to produce clean results. So it's there as opposed to just saying, hey, I've got these depth readings and let's just throw them into 3D space and hope that they align, or hope that they're not noisy. We're doing volumetric reasoning, trying to figure out, okay, well, I've got all of these different depth measurements of a surface, where is that true surface? And, fusing those different depth values together. And so that's where we get the benefit of, that raw LiDAR data, that raw depth data may have been noisy. There may have been some misalignment. Our image-based depth maps may have missing parts, like you said, like that shiny car. It's really shiny and reflective. We're gonna have a hard time reconstructing that using images alone. But by combining these two sources of data together and figuring out, well, where is that actual surface, we're able to produce these, really, really nice, clean results.
Okay. What about the sensors, like the I don't know if they're accelerometers, it's the IMU, or like whatever it is that whatever magic black box they've got in there in the iPhone. It seems to be just looking at it and doing some scans with different things. I'm surprised at how robust the thing is. So have you seen like an improvement over the years? Is this something that you've been paying attention to, or just more recently that you've started to look at this type of data? But is that something that is helping you in the calculation, or something that you're leveraging?
Yeah, absolutely. And so I think two of your things. Okay, so many years ago, I wasn't paying as close attention to the sensor data in there, but I have definitely seen improvements. So over the recent years, especially since ARKit's been released, so ARKit being Apple's SLAM engine that does the 3D pose estimation on device. The sensors, at least the sensor data that I'm getting out of there has been better and more easy to use. And so we're able to use that as part of the algorithms to provide additional robustness. So for instance, that inertial sensor data, like the accelerometer is always telling you, which ways, gravity, or you can decompose it. It's always telling you acceleration. You can decompose that into a gravity direction as well as sort of a user-induced acceleration, so we can use that to help, improve the results as well as detect artifacts. So one of the things, we've done is, if we're detecting high acceleration or using the gyroscope to detect high rotations, we can use that to help guide the user and say, hey, hold on, it seems like you're shaking the phone a lot, or you're moving pretty quickly, or might be rotating in place. You might want to, slow down, take a breath, try that again. And so it's both for feedback as well as, as an input into the photogrammetry algorithms to help provide additional constraints and information about how that camera moved through the space.
That's a great point you brought up, because it was something that was apparent to me. But when you're doing a photogrammetry project, oftentimes there is no orientation in terms of what is gravity or plumb. So your reconstructions sometimes will end up on an angle, or they're not correct. And it's true, all the stuff that I'm getting out of the phone right now, and I just noticed it. Everything's flat. Everything looks level. And I'm like, hey, damn, like that's pretty good. So now I don't know how true it is, but certainly something that looks to the eye to be relatively level. So that's pretty cool there. Let me ask you about this is obviously relatively new. The 12, I think, came out in 2020. Was it 2020, 2021 maybe? I don't remember when the 12 with the LiDAR came out first, but it's new. So are you seeing the potential of other things that could be implemented into something like this going forward?
Potential other things being implemented to this. Are you saying like other uses for the LiDAR, like this depth sensor?
Well, what I mean is like the ability to improve it even further with, I don't know, maybe like artificial intelligence, different types of computing that you're going to throw at it. I don't know. Is there? I'm just curious to know how possible it might be to grow this, or to expand it, to make it even more accurate, to make it faster, to make it whatever.
Oh yeah. No, we're definitely just scratching the surface. There's both from hardware through software through the whole stack. Because you're touching on machine learning. So I said. So with the Apple's LiDAR sensor, okay, yeah, it is outputting this, I say, 256 by 192 pixel depth map, but that in itself is leveraging machine learning. The underlying hardware, that physical sensor, is a much lower resolution sensor, and so that there's a sparser set of depth readings that are being returned, but those depth readings are being upsampled to this 256 by 192 depth map using machine learning. So it takes those depth readings from the physical sensor plus the RGB pixels from the camera, so that the color information, and then does some machine learning to say, okay, well, let me upsample, let me resample, let me infer or interpolate, what those depths are. So there's opportunity there for those algorithms to be better. I'll say on Apple's side, that's all inside of Apple's black box. Opportunity for that to get better, and I see that will be getting better with better techniques, better sensor, better hardware. There's also opportunity, for the reconstruction side. As we start to continue to use this data more, and as the machine learning community continues to advance, there's opportunities to say, okay, well, I've got this image-based data, I've got LiDAR data, and how can we better fuse that together and figure out, well, which one is more accurate or more useful? Because there are pros and cons. There's cases when images may not give you depth readings, or images might get confused if there's reflections. If I've got water or a mirror, that image, that reflection is going to give me incorrect depth readings. And so both of those, both your images and your LiDAR are going to get confused. But there's opportunity to leverage machine learning, for instance, on the imagery and say, hey, that looks like a reflective surface. I shouldn't trust those depth readings. And there's just different ways that I think as we continue to dig into the data, we're going to find there's lots of different ways that we can leverage the best of both worlds, plus machining or other techniques to make it better.
We've been talking about the iPhone, but I'm just curious if in the future, you never know, maybe Samsung or somebody else may implement a LiDAR sensor as well. But what about like an external sensor? Like right now, Intel has their depth sensors, the RealSense family of sensors. I'm just curious, is that something that you could leverage as well? Maybe not on the phone, but you'd have something that could provide you depth and then use something else that could give you photogrammetry. Does it matter where the input source comes from?
Not really, no. Because from an algorithm standpoint, at least how we've approached it, it's saying, hey, I've got imagery, I've got depth readings, I've got some sensor data. I'll use whatever I can get, to generate that best fused result. And so if it was an inbuilt LiDAR sensor or something that you strapped onto or attached to your camera that was providing you that additional depth data, certainly there's definitely opportunity to leverage things like that.
No, it's pretty cool. Yeah, definitely some things to look forward to. I do want to ask you about something else, and that has to do with some of the other work that you've done. And you did some work with augmented reality and looking at tactical visualization and stuff like that. Can you tell me about some of the AR stuff that you were working on?
Oh man, so I think I'm guessing you're referring to some of the work that I did back during grad school.
Yeah.
With the visualization. So with that, I worked on a very small piece of that. So the end goal was to provide a user with an augmented reality overlay where they could see out in the real world. They're out in the mountains, they're out just in a field, they're out wherever, but to be able to identify positions or locations, and just provide a nice, heads up display, for tactical or, other purposes. So the work that I was doing there was trying to figure out how can you determine the user's absolute orientation when you don't have, like a compass, like you're in some sort of sensor divided environment, or like your magnetic compass isn't accurate enough. You need really, really accurate orientation without using other sensors. And so the work I was doing there was terrain matching. So assuming that I had a camera, mounted to the person's head as they moved around, I would look for geographic features within that image. So mountain peaks or ridges or hills, and match that against, an elevation map for the region that they were in. So I would download and say, okay, you're going to be in this location. Great. I'll download all the elevations, an elevation map of that terrain. And then as you walk around, try to do that terrain matching to get really accurate orientation. So yaw, roll pitch yaw, 3 degree of freedom, right. Orientation estimation off of that terrain.
That's cool. Cool stuff. So never know, maybe one day you'll be doing that with the AR. With the AR and all the 3D data you're capturing. Obviously there's a an application to augmented reality and to virtual reality as well. But yeah, never know. There's a big push in that area. I'm still, sort of cautiously optimistic with the VR stuff. I'm not. There's still, I think, quite a ways to go. But yeah, I think some of the work that you're doing is excellent. The sensor fusion with the, what you guys have been doing at EveryPoint is really awesome. Really, I think causing a stir as a new technology. And so kudos to you and the team for doing some great work.
Yeah, thank you.
All right. Well, look, thanks so much for your time. I really appreciate it. Great talk, great information, great insight. So, hey, as always, thank you very much.
Thanks, Gene.
All right. Bye-bye.
Bye.